All right, this is video 4 of week 11 for CS 499 Network Science with Dr. Vigil-Hayes. So in the last video, we talked about using um, the degree correlation exponent as a way to quantify whether or not um, a network was assortative or whether it was disassortative or neutral. So in this video, what we're going to kind of go over is whether or not it's possible to generate networks intentionally that have properties of assortativity or disassortativity. So the big question that we're going to try to tackle is it possible to generate networks that are assortative or disassortative? So as a starting point, let's start by looking at models that we have already studied. So the static models that we've talked about are the Erdős-Rényi model, the configuration model, and the hidden parameter model. We've also talked about Watson-Strogatz and wow, I am totally blanking on the name, the degree preserving model. Of course, I forgot the name because it's not even a real network generator, right? I always joke about that. So if we look at these different models, especially for Erdős-Rényi configuration and hidden parameter, if we look at different running it with different parameters, running these models, generating different networks, we find that in general, Erdős-Rényi will generate neutral networks, and this should not be surprising, right? Because these are networks that are forming links between nodes completely at random, has nothing to do whatsoever with node degree. The configuration model, if multi-links and self-loops are allowed, this tends to generate a neutral network. And if it is just a simple version of the model, so multi-links and self-loops are not allowed, this model tends to generate disassortative networks. And then for the hidden parameter, similar to the configuration model, so remember the hidden parameter model specifically prohibits and addresses this issue of multi-links and self-loops. This also generates a disassortative network. And again, this should kind of make sense. So if multi-links and self-loops are allowed, it should make sense that the network would be neutral because there's really there's nothing about node degree that dictates whether or not nodes are actually going to be connecting. And then for the hidden parameter model, so remember we're assigning a hidden parameter to each node. Because we are looking at a product of probabilities, if two nodes have a high probability or a high hidden parameter model associated with them, it's then going to be less likely that they're going to form a connection between each other. So next, on to the evolving models. So remember we have Barabasi-Albert, which just takes in n as the final number of nodes that will be in the network, and m naught, which is the initial number of nodes in the network, and also m, which is the number of nodes that a new node coming into the network will attach to. And so a Barabasi-Albert model will generally generate a neutral network. So, in the early kind of formation of nodes, even though it's likely that most nodes as they join in early are more likely to become hubs, sometimes those hubs will early on be attached to each other, but as the network kind of iterates through, it's less and less likely that you will have hubs connecting to each other. So over time, this generates kind of a neutral network. If we look at Bianconi-Barabasi, so remember this is where we have that fitness parameter that's also being integrated into the model, we tend to generate disassortative networks. So this is kind of what the existing models already yield, and it's very difficult to parameterize these models in such a way that you can really influence the assortativity. So it's kind of like no matter what the parameters are, they're going to have these fall into these classes of structural assortativity. So this kind of brings us to our next question of whether or not it's possible to generate networks that are assortative. And to do this, we have a new algorithm to generate a network. So this is called the Xulvi-Brunet and Sokolov algorithm. And it kind of just is very elegant. It consists of two steps that are repeated over and over. And the more frequently these steps are repeated, the more kind of extreme your assortativity or disassortativity is going to be. So in the first step of the algorithm, well, I guess in step 0, so before we even start, we're going to start off with maybe a random network. So maybe we'll use something like Erdos-Renyi, or we'll use Barabasi Albert. We'll generate some network to start with. And then we're going to use this algorithm to push that network into either being assortative or disassortative. So in step 1, what we're going to do is we are going to choose 2 links at random. So that means we'll have 2 links, and then we'll have 4 nodes that are consisting of the endpoints for those links. And we will order the nodes so that their degrees are ordered such that the degree of node A is greater than or equal to the degree of node B, and the degree of node C is greater than or equal to the degree of node C, and the degree of node D is greater than or equal to the degree of node C. So we're kind of just ordering them according to their degree values. And then what we're going to do in step 2 is rewire. So if we're rewiring, we're going to break the selected links and we're going to rewire them to form new pairs. And this is going to depend on the desired degree correlations that we're wanting to create. So if we're wanting to create an assortative network, we're going to pair the 2 highest degree nodes and the 2 lowest degree nodes with each other. So let's say we have, this ordering where node A has the highest degree and then node B has the second highest degree. Well, we're going to rewire such that node A and node B are connected to each other. It may be that in rewiring, we actually just create exactly the same link that we had originally. That's totally fine. But that's how we're going to rewire. And then we take the 2 lowest degree valued nodes and we rewire the link between them. So in this way, it's assortative, right? We're trying to pair degree values or nodes with degree values that are higher with each other, and we're trying to pair nodes with lower degree values with each other. So in the other fork, so it's kind of step 2B, if we're creating a disassortative network, what we're going to do is pair for our rewire the highest and lowest degree nodes, and then we'll connect nodes that have, so we'll kind of do the 2 edge extremes, and then we'll do the 2 in between value nodes together as well. So if we repeat this process either for the assortative or the disassortative style networks, if we complete step 1 and step 2 over and over, if we do it kind of an infinite number of times, we will approach the point where we've created networks that either are perfectly assortative or perfectly disassortative. And of course, as n and e, so the number of edges, or L, the number of links, as those values increase, it's going to require more and more steps in order to get to that perfect assortative or perfect disassortative state. But, there's another way where we might want to mix it up. It may be that we aren't exactly going for, assortative or disassortative in the extreme, but maybe we want to just kind of tend towards assortative. So we want to generate a network that's kind of like a real network, right? So, um, we're going to have a tendency towards assortative, but we're not going to be perfectly assortative. Um, so the way that we do that is just a simple modification to the Xulvi-Brunet and Sokolov algorithm. So what we're going to do is we're going to start really similarly. We will have our initial network, and then remember, we still have this kind of these two different steps where we're either rewiring for assortativity or we are rewiring with disassortativity. But what we're going to do is introduce this randomization step. So what we're going to do is add a random parameter, and we're going to add a second type of rewiring. So the first type of rewiring that we do is the normal assortative or disassortative rewiring that we talked about for the original algorithm. But the second is a random rewiring, where we randomly pair the 4 selected nodes with each other to form two new links. So it's completely random. And we have this p-value, which we've kind of talked about different styles of p-value random parameters before, where, if let's say p is 0.25, well, if we have, if we were to kind of do our random number generator and we had a number between 0 and 0.25, then we're going to go ahead and do the normal assortative or disassortative rewiring process. But if we were to get a value greater than 0.25, then we would instead do the random rewiring. And so what this would look like, if we were to kind of use these different p-values to generate these different models, we can see how it would impact the level of assortativity. So here we have 2 graphs, one for the assortative case, one for the disassortative case. Each kind of set of dots, each color represents a different p-value. And we're graphing this on a degree correlation graph. So we have the degree of a node in the x-axis, and we have the average degree of a node's neighbors in the y-axis, right? So really similar to the types of networks that we've seen before. And what we're actually going to be looking at is kind of the beginning first parts of these distributions. So if we were to look at the initial start of each of these distributions, what you'll probably notice is that as p for the for the assortative network, as p gets larger, we're going to increase our exponent. So remember, because this is on a log-log scale, as our slope gets a larger and larger positive value, that means that our exponent is getting a larger and larger positive value. And that means it's more and more assortative. On the flip side, for a disassortative network, as p gets larger and larger, we tend to have a steeper and steeper negative slope. So again, this is going to represent the case where, we have this log-log axis situation going on. As we get an increasingly negative slope, that's going to correspond with an increasingly negative exponent, and that is going to be kind of leaning more and more towards a perfect dissociative network. So that is the end of the models that can generate dissociative and assortative networks. We can always generate a neutral network using Erdős-Rényi. We know how to do that quite well. And yeah, for the rest of the lectures in terms of new material, I'll just be talking about how these different types of networks kind of fall into the different kind of regimes, network regimes that we've been talking about.